Alright, this is my submission for homework 4. I apologize for the latency. I kind of got caught up with a lot of work for other classes when this was due. So I am doing it now to submit. So let's get started. Let's see. So this is the problem statement, and we're asked for two things. It says water from a 3-meter tall, 30-meter diameter holding tank flows vertically down from 7-meter length of 1-meter diameter pipe into bottom of massive gold-plated jacuzzi. Okay, so first thing that we need to do is go ahead and draw a diagram for this. So I'm going to start with the holding tank. And we know that this is 3 meters tall. Say this is our water level. And we'll label this at 0.1. And this is going to flow down to the jacuzzi, which let's just put our jacuzzi right down here. And we know that our jacuzzi is one meter tall. Yep, 1 meter tall. And we're going to have a pipe flowing vertically downwards going into the bottom of the tank. And this we're going to label at 0.2 of our system. And we're also given that this is a 7-meter length of pipe. So from here, this point to the bottom of this tank is 7 meters. And then also we're given that it's pumped back up by a 100% efficient pump to this holding tank. So if this is our pump here, it's pumped from the bottom of the tank up to here and back into the holding tank. And we're going to label this at 0.4 and this at 0.5. Okay, we're also given that the diameter of the nozzle, there's a nozzle here at 0.2. The diameter is 10 inches, so I'm just going to do the radius of 5 inches. The pipe has a diameter of 1 meter. I'll label that here. Equals 1 meter. Yeah, all of these are 1 meter. Okay, so we're given, that's our situation, that's what we're given. And it says, if the pump is perfectly insulated, and transfers no heat to the water, is a chiller necessary to keep the water at the same temperature? And also, it wants to know how much power the 100% efficient pump requires. Okay, so first thing we need to find the power. And we know that this has to be a steady flow, open system. This is exposed to the environment right here. So what we can do is we can do our equation that there's we need H plus GZ V squared over 2 out. This is the equation for steady flow open systems. And that is dq over dm plus the work, the non-flow work, over the change of mass. Okay, so from point, we're going to solve this in parts. We're going to do from point 1 to point 2, and then from point 4 to point 5. So essentially we're going to have 3 parts to this. We're going to have, so part 1, that's going to be from 1 to 2, and then we're going to have part 2 from 4, actually, Yeah, I'll just label this 4 because 3 is like an intermediate. So from 4 to 5, 3 is just kind of chilling, you know, chilling in the jacuzzi. It's a dummy mistake, misnumbered it, but it's cool. We'll go with it. And then part 3 is just going to be us solving for power. That's kind of where we're at with this. That's our plan. So with this equation, to find h here, we can do P2 minus P1 over rho to give us that, and then plus G times Z2 minus Z1. I'm just going to kind of combine these. This is out and this is in, so I'm just going to combine them, make it all one thing. Then we're going to do plus V squared, or V2 squared minus V1 squared over 2, and our flow rate isn't going to change from that. It's going to stay the same. It's all in the same pipe here. So, and also we don't have non-flow work, so this is going to be equal to 0. And P1, the pressure P1, we can assume that to be 0 because it's open to the environment. That's negligible. So, and then pressure we know is rho GH. So we're going to have rho GH minus 0 over rho here. This rho is going to cancel. So then we're going to be left with GH. So GH. Okay. And this is from point, the H here, right there, is going to be from this point here down, because this is like the only part that matters is where it's in the water. So that's going to be 1 meter. So technically we're just going to be left with GH. So GH plus G, and actually I'm just going to go ahead and fill values in. So we're going to have, like I was saying, 1 G plus G times Z2, the height at 2, which is 0 right here. So 0, and let's see, Z1, which is going to be 10 because the height of the tank is 3 meters. Height of the pipe is 7, so this is the bottom, so it's 10. So 10 plus V2 minus V1. Now V1 is a very big tank. Like the holding tank it's very large in diameter. It says it's 30 meters. So V1 velocity at that point is negligible compared to what we're already solving for at V2. So we can just approximate that at 0. So plus V2 squared over 2 is equal to 0. And so here we can get negative 9G plus V2 squared over 2 is equal to 0. And now we can solve for V2. That gives us an unknown. So then we can have V2 is equal to square root of 18G. So that's part 1. Part 1 done. That gives us the unknown there. And now for part 2 from 4 to 5 is essentially the same thing. The difference here is that we're not going to have this term. That's just going to cancel because this pump is going to be pumping it from here to here, so all of this has to be moving at the same velocity. It's not like this one, it was at it was open to the environment, so it mattered. But this one, they're both in the pipe and they're the same velocity, so it's just going to cancel. So we're going to have, like I said, kind of the same equation. So P5 minus P4 over rho plus Z5 minus Z4. And here, because we have the pump, we're going to have non-flow work. So work non-flow over mass. We know that Z5 to Z4 is from the top to the bottom again, but the difference here is that it's flipped. We're going the opposite direction, so this is going to be 10. So 10G there. And P5 and P4 are the same. Hold on, wait a second. Yeah, P5 and P4 are going to be the same for this circumstance. But the difference is the fact that here, actually this is going to be not going to be 10G, that's going to be 9G, because we're worried about this guy. It's being pumped out of here. This is pumped out of the top. So this is going from this point, so not there, from this point up to the top. So that's 9. So this is going to be 9G is equal to the non-flow work. So that gives us another unknown here. And the power equation, so that's part 2. So part 3 is actually going to be calculating the power, and we know that the power equation, power is equal to m dot work non-flow over mass. And we've got this guy here, so we can plug that in, but we don't have this. Lucky for us, we know that mass flow, so I'm just going to rewrite the equation, but mass flow is density times volumetric flow. And Q is equal to VA. And the one thing is, since Q is equal to VA in this situation, we're looking for work non-flow for the pump, or the power for the pump rather, and there's no, like we're going to be bottled down by this point here. That's going to be the point that we refer to here, which is nice because we just solved for that kind of stuff, like for Q equals VA. So we know that power is going to equal V2 rho V2 A2. I'm going to go ahead and plug this in, 9G. And so first what we can do is go ahead and solve for this term. And we're going to have, we know that the radius of the pipe or the nozzle at 0.2 is 5 inches. So 5 inches times 2.54 centimeters, just converting things here to meters, that way they're all the same. And we can get it in watts. So 1 meter 1,000 centimeters. That gives us a meter there, and that's going to be equal to 0.127 meters. So that's our nozzle diameter. And then we know that the density of water, rho, is 1,000 kilograms per meter cubed times our cross-sectional area here, so A2. That is going to be 0.127 meters squared pi, and then times V2, which is square root of 18g. We solved for that up here. So square root 18g. And that's going to be multiplied by 9g, which is our work non-flow over mass. Just plug in values in there. And then from that, we're going to get that the power, this bad boy, right here, is going to be equal to 59,448.3 watts, or 59.4, I'm just going to round, 45 kilowatts. Now, the second question, it asks, if the pump is perfectly insulated and transfers no heat to the water, is a chiller necessary to keep the water at the same temperature? And no, a chiller would not be necessary to keep the water at the same temperature. It's open to the environment. That's going to be one factor, and that's the only thing that's really going to be affecting the temperature of the water, since this is perfectly insulated. And since it's cycling through this entire system, I mean, that's good enough. There's no chillers necessary. And that's it.